The human eye that enables us to view is a very complex organ. Let us first study its structure. The white protective membrane that is seen when looked at the eye directly is called the sclera. It is a tough, opaque, fibrous outer layer of the eyeball. The circular colored part is called the iris. The color of the eye is determined by the color of the iris. The central transparent area of the iris is called the pupil. The iris works like the shutter of a camera. It absorbs most of the light that falls on it and allows a part of it to pass through the pupil. The amount of light that enters the inner parts of the eye depends on the size of the pupil, which is controlled by the muscles present in the iris. In bright light, the iris contracts the pupil to restrict the light, whereas in dim light, it widens the pupil to admit more light into the eye. The eyeball that contains different parts of the eye is roughly spherical in shape with a diameter of 2.5 centimeter. A transparent protective membrane called the cornea covers the small bulged portion at the front of the eyeball. In fact, the iris and the pupil lie behind the cornea, the crystalline lens, and the retina are some of the other important parts of the eye behind the cornea. The crystalline lens is held in its position by the ciliary muscles. The retina is a film of nerve fibers covering the curved back surface of the eye. It detects the presence of light and its color and sends this information to the brain through the optic nerve for further processing. The retina is able to detect the light and its color because of the presence of sensors called rods and cones. The rods are sensitive to low light, whereas the cones, which require a greater intensity of light, are sensitive to color. The portion between the cornea and the lens is filled with a watery fluid called the aqueous humor. The space between the lens and the retina is filled with a jelly-like fluid called the vitreous humor. Now let us study the working of the human eye. Light entering the eye is first refracted by the cornea. The refractive power of the cornea is large and fixed. The refracted light is then incident on the iris. The crystalline lens is just behind the iris, and light after passing through the pupil falls on it and is again refracted to form a sharp image on the retina. For an object to be seen clearly, the image must be formed exactly on the retina. The crystalline lens along with the cornea is able to refract the light that enters the eye to form a sharp image on the retina. The eye is able to focus objects at different distances sharply on the retina by changing the focal length of the crystalline lens. The process of adjusting to different object distances by changing the focal length of the crystalline lens is known as accommodation. Ciliary muscles help in adjusting the focal length of the crystalline lens. Ciliary muscles are in relaxed state when an object at infinity is sharply focused on the retina. In this case, the focal length of the crystalline lens is the maximum and is equal to the diameter of the eye. When the object is close to the eye, the tension in the ciliary muscles increases and the lens becomes more bulged with reduced radii of curvature. The reduction in the radii of curvature of the crystalline lens reduces its focal length also. But the focal length of the crystalline lens cannot be reduced beyond a limit. Hence, there is a limit for the closest distance for which the lens can focus light on the retina. This is called the least distance of distinct vision, or near point, represented by the letter D. Usually the value of D is taken as 25 cm for a normal eye. The greatest distance for which the lens of a relaxed eye can focus light on the retina is called the far point. The far point of a normal eye is at infinity. We can summarize the three important functions of the eye as follows: admitting appropriate amount of light, refracting the light to form a sharp image, collecting and sending information about the image to the brain for further processing. Now let us discuss some common optical defects in the human eye. The most common defect of the human eye that is found in aged persons is presbyopia. The ability to focus on near objects diminishes with age. This is known as presbyopia. The near point changes with age. For a 10-year-old boy with good health, the near point may be about 7 to 8 cm. This changes with age and may even reach 2 meters for an old person of the age of 60 years. Hence, aged people cannot see objects placed at normal distances of about 25 cm. The incoming light rays are refracted to focus behind the retina. Presbyopia can be corrected by using an appropriate converging lens. Another vision defect that is similar to presbyopia is hypermetropia, or farsightedness. Note that presbyopia is caused by old age, whereas hypermetropia is a vision defect that can be observed in persons of any age. A person suffering from hypermetropia will have normal vision when looking at objects at the far point. But the objects that are close to the eye are focused behind the retina, and as a result, vision is blurred. The defect caused by hypermetropia can be rectified by using a convex lens of appropriate focal length. When a converging lens of suitable focal length is used to rectify either presbyopia or hypermetropia, the image of the object is formed at the near point of the person. For example, let us find the power of the corrective lens used by a person suffering from hypermetropia with near point at 2 meters. Given that the near point of the person is 2 meters, but for a normal person the near point is 0.25 meters. In case of the person suffering from hypermetropia, an object placed at 0.25 meters is focused behind the retina. If a corrective lens is used, it must form the image at a distance of 2 meters. This image will act as an object for the eye lens. That means if U is equal to 0.25 meters, then V must be equal to 2 meters. Substituting these values in the lens formula and solving for the optical power, we get power P is equal to 3.5 diopter. Another commonly observed eye defect is myopia or nearsightedness. An optical defect in which distant objects appear blurred because their images are focused in front of the retina is called myopia or nearsightedness. The person suffering from myopia will have perfect vision when looking at objects close to the eye. But in the case of an object at a faraway place, the eye produces more than required convergence, and as a result, the image is formed before the retina. The effects of myopia can be reduced by using a concave lens of suitable focal length. A defect of vision caused when the cornea is not spherical in shape is called astigmatism. Because of the non-spherical cornea, the eye lens will have different curvatures in different planes. Light in one plane is focused properly on the retina, and objects in that plane are visible clearly. Light from a perpendicular plane is focused at a different location other than the retina, resulting in blurred view of the objects lying in that plane. Hence, a person suffering from astigmatism cannot see all directions equally well. Astigmatism can be corrected by using a cylindrical lens of desired radius of curvature with an appropriately directed axis. We know that light rays, when incident on a lens, converge in the case of a convex lens and diverge in the case of a concave lens. The degree of convergence or divergence depends on the focal length of the lens. If the focal length of a lens is small, then the convergence or the divergence of light is more. On the other hand, if the focal length of the lens is high, then the convergence or the divergence is less. The physical quantity, that is a measure of the convergence or divergence of light introduced by a lens, is called its optical power. The optical power of a lens is defined as the tangent of the angle by which it converges or diverges a beam of light falling at a unit distance from the optical center. You know that a light ray, when incident parallel to the principal axis, after refraction by a convex lens, passes through its principal focus. If the ray is incident at a height h from the pole, and the deviation of the light ray or the angle through which the light ray converges is d, then tan d is equal to h by f. If h is equal to 1 unit, tan d is equal to 1 by f. But as per definition, tan d for h equal to 1 unit is the power of the lens. Therefore, optical power P is equal to 1 by f. That means optical power of a lens is the reciprocal of its focal length. The SI unit of optical power of a lens is dioptra and is indicated by D. Power of lens is 1 dioptra if its focal length is 1 meter. Power of a lens can be positive or negative. As per the Cartesian sign conventions, focal length of a convex lens is positive and that of a concave lens is negative. Hence, the power of a lens is positive for a converging lens and negative for a diverging lens. Note that the focal length and hence the optical power of a lens depends on the medium in which the lens is placed. For example, a converging lens in air with focal length equal to 20 cm is made of glass of refractive index 3 by 2. Let us find its optical power when placed in water of refractive index 4 by 3. It is given that refractive index of glass Ng is equal to 3 by 2. Focal length of the lens in air f equal to 20 cm or 1 by 5 meter. According to the lens maker's formula, 1 by f is equal to Ng minus 1 into 1 by R1 minus 1 by R2. Substituting the values of f and Ng in the equation and on further simplification, we get 1 by R1 minus 1 by R2 is equal to 10 per meter. Let the focal length be f dash when the lens is placed in water. Then, according to the lens maker's formula, 1 by f dash is equal to Ng by Nw minus 1 into 1 by R1 minus 1 by R2. On substituting the above values and on further simplification, we get 1 by f dash is equal to 1.25 per meter. That means the power of the lens in water is equal to 1.25 dioptra. Therefore, the optical power of the given lens in air is 5 dioptra, and when placed in water, it is changed to 1.25 dioptra. Many optical instruments use a system of combination of lenses in order to get the required magnification and to enhance the sharpness of the picture. Let us now derive an expression for the effective focal length of a combination of two thin lenses A and B with focal lengths FA and FB placed in contact with each other coaxially. Let a point object O be placed at a distance u from the first lens A. Since we deal with thin lenses, all distances can be measured from the contact point of both the lenses, S. This is because, in such a situation, the optic centers of the two lenses will coincide with S. If there were only one lens, A, the image of the point object O would have formed at I'. Let the distance of the image be V1. Using the thin lens formula, we can write that 1 by FA is equal to 1 by V1 minus 1 by U. Let this be equation 1. If the presence of the second lens is also considered, the final image will not be formed at I'. Let us analyze the refraction through the second lens. If a diverging beam of light is incident on a lens, then the object is a real object. On the other hand, if a converging beam of light is incident, then it is treated as a virtual object. Hence, for the second lens, I' acts as a virtual object. The ray of light is further converged to form an image at I. If the image I is at a distance V, then 1 by FB is equal to 1 by V minus 1 by V1. Let this be equation 2. By adding equations 1 and 2, we get 1 by FA plus 1 by FB is equal to 1 by V minus 1 by U. Let this be equation 3. For the system of two thin lenses in contact, U is the object distance and V is the image distance. If F is the effective focal length of the lens system, then using the thin lens formula, we can write that 1 by F is equal to 1 by V minus 1 by U. Let this be equation 4. From equations 3 and 4, we can write that 1 by F is equal to 1 by FA plus 1 by FB. Let this be equation 5. Since optical power of a lens is the reciprocal of its focal length, we can rewrite the equation 5 in terms of the optical powers as P is equal to PA plus PB. Let this be equation 6, where P is the net optical power of the combination of two lenses with individual powers equal to PA and PB. For a system of n lenses in contact, we can write equations 5 and 6 as 1 by F is equal to 1 by F1 plus 1 by F2 plus so on up to plus 1 by Fn, and P is equal to P1 plus P2 plus so on up to plus Pn. In case of a system of lenses, the image formed by one lens is the object for the next lens. Hence, the total magnification of the combination is a product of the magnifications of the individual lenses. If the magnification of the combination is M and the magnification of the individual lenses are M1, M2 and so on up to Mn, then M is equal to M1 into M2 into so on up to Mn. While using these equations, it is important to note that proper sign convention is to be applied for the values of focal length and optical power. Let us look at an example to understand this better. If a convex lens of focal length 10 cm is in contact with a concave lens of focal length 15 cm, how does the combination work? According to the Cartesian sign conventions, we have focal length of the convex lens f1 equal to 10 cm and the focal length of the concave lens f2 equal to minus 15 cm. If f is the focal length of the combination, then 1 by f is equal to 1 by f1 plus 1 by f2. Substituting the values of f1 and f2 and after simplification, we get f is equal to 30 cm. Since the effective focal length is positive, the combination of the given lenses act as a convex lens of focal length 30 cm. If these two lenses are separated by a distance of 10 cm and a point object is placed at a distance of 15 cm before the convex lens, where does the final image get formed? In this case, in addition to the focal lengths of the two lenses, it is also given that the distance between the two lenses, d, is equal to 10 cm and the object is at a distance of 15 cm. First, let us find the position of the image I1 formed by the convex lens only. Let the image distance be V1. On substituting these values in the thin lens formula and solving for V1, we get V1 equal to 30 cm. Hence, the image is formed at a distance of 30 cm from the convex lens. Now introduce the concave lens between the convex lens and the image I1 at a distance of 10 cm from the convex lens. The image I1 formed by the first lens serves as the object for the second. This distance U1 is 20 cm to the right of the concave lens. Since it is to the right of the lens, its value is positive. If the final image is at a distance V from the concave lens, then 1 by V is equal to 1 by F2 plus 1 by U1, or V is equal to U1 F2 by U1 plus F2. On substituting the values of U1 and F2 and solving for V, we get V as equal to minus 60 cm. The negative sign indicates that the final image is formed to the left of the concave lens at a distance of 60 cm. Note that the virtual object is in between F and 2F of the concave lens, and hence the rays are diverged to form an image to the left of it. Lens is a transparent material bound by two surfaces, of which at least one is spherical. Lenses are classified based on the curvature of the spherical surfaces. Two of the most useful lenses are the double convex lens and the double concave lens. If both the surfaces are convex, the lens is called a double convex or a biconvex lens. And on the other hand, if both the surfaces are concave, then the lens is a double concave or a biconcave lens. The central point of a lens is called its optical center. Since there are two spherical surfaces, a double convex lens or a double concave lens has two centers of curvatures. C1 is the center of curvature corresponding to the first curved surface having radius of curvature R1. C2 is the center of curvature corresponding to the second curved surface having radius of curvature R2. The straight line joining C1 and C2 is the principal axis of the lens. If the thickness of the lens is very small compared to other measurements, such as object distance or image distance, etc., it is called a thin lens. A ray of light incident on a double convex lens or a double concave lens undergoes refraction at each of the spherical surfaces. In case of a double convex lens placed in air, the light ray bends towards the normal, C1N1, at the first spherical surface, and bends away from the normal, C2N2, at the second surface. Paraxial rays parallel to the principal axis incident on a double convex lens, upon refraction, converge to a point on the principal axis. This is called the second principal focus of the lens. Principal focus towards the source of light is called the first principal focus of the lens. In case of a double concave lens, the incident ray bends towards the normal, C1N1, at the first interface, and away from the normal, C2N2, at the second interface. when a parallel beam of light rays is incident on a double concave lens. Upon refraction, it appears to be diverging from a point on the principal axis, and such a point is called the second principal focus. Note that if we merely mention principal focus, it means we are referring to the second principal focus. The distance between the optical center and the principal focus is called the focal length f of the lens. Let us now study the images of an extended body formed by a lens. To locate the image by drawing a ray diagram, we usually trace the path of any two of the following rays. Light ray that is parallel to the principal axis, after refraction, passes through the second principal focus in case of a double convex lens, and appears to diverge from the second principal focus in case of a concave lens. If a light ray is directed towards the optical center of a lens, then it passes through the lens without any deviation. If a light ray passes through the first principal focus of a convex lens, then after refraction it passes parallel to its principal axis. In case of a double concave lens, if a ray of light appears to converge onto the first focal point, then after refraction it becomes parallel to its principal axis. Now, observe the image formation in case of a convex lens when an extended object is placed at different positions. In the case of a double concave lens, the image formation for various positions of the object is as shown. Observe that the double concave lens always forms a diminished virtual image, and as the object is moved towards the lens, the image also moves in the same direction. The images formed by a lens can also be explained mathematically as follows. Consider a double convex lens AB made of material with refractive index N2 and placed in a medium of refractive index N1. Let C1 and C2 be the centers of curvatures of the two spherical surfaces ADB and AEB with their radii of curvature equal to R1 and R2 respectively. If a point object O is placed on the principal axis, its image is formed at I. Let U be the object distance and V be the image distance. The refraction of light through the lens can be split into two steps. In the first step, let us consider the refraction at the first spherical surface ADB. Because of this refraction, a real image of O would have formed in the second medium at I1. According to the Cartesian sign convention applicable for refraction at spherical surfaces, measurements are taken from the intersecting point of the spherical surface and the principal axis. Let DI1 be V'. Since we consider only thin lenses, DO is equal to U. We know that the relation between object distance U and image distance V for the refraction at a spherical surface is given as N2 by V minus N1 by U equal to N2 minus N1 by R, where R is the radius of curvature for the curved surface. Using this, we can write that N2 by V' minus N1 by U is equal to N2 minus N1 by R1. Let this be equation 1. In the second step, let us consider the refraction at the second spherical surface AEB. Because of the refraction at AEB, the image is actually formed at I instead of forming at I1. Since the lens we are dealing with is a thin lens, we can write that EI is equal to V and EI1 is equal to V dash. Hence, we can write N1 by V minus N2 by V dash is equal to N1 minus N2 by R2. Let this be equation 2. On adding equations 1 and 2, we get N1 into 1 by V minus 1 by U is equal to N2 minus N1 into 1 by R1 minus 1 by R2. This can be written as 1 by V minus 1 by U is equal to N2 by N1 minus 1 into 1 by R1 minus 1 by R2. Since N21 is the refractive index of the second medium with respect to the first medium and is equal to N2 by N1, we can write 1 by V minus 1 by U is equal to N21 minus 1 into 1 by R1 minus 1 by R2. Let this be equation 3. If the object is at infinity, the image will be formed at the second principal focus. That means, if U is equal to infinity, then V is equal to focal length f. Therefore, equation 3 can be written as 1 by f is equal to N21 minus 1 into 1 by R1 minus 1 by R2. Let this be equation 4. This equation is known as lens maker's formula. If we observe equations 3 and 4, the right side of both the equations are identical. Hence, we can equate the terms on the left. Doing so, we get 1 by f is equal to 1 by V minus 1 by U. This equation is known as thin lens formula. Now place an object OJ of height h before a double convex lens. Let IG be its image and of height h dash. Since the two triangles POJ and PIG are similar triangles, we can write that IG by OJ is equal to PI by PO. But IG is equal to minus h dash. OJ is equal to h. PI is equal to V. And PO is equal to minus U. On substituting these values in the above equation, we get h dash by h is equal to V by U. But linear magnification M is equal to h dash by h. Therefore, in case of a thin lens, the linear magnification M is equal to V by U. Lens maker's formula is useful in calculating the required curvatures to make a lens of desired focal length. Note that N21 is the refractive index of the material of the lens with respect to the refractive index of the medium in which it is placed. R1 is the radius of curvature of the first spherical surface on which the light ray is incident, and R2 is the radius of curvature of the second spherical surface. It is also very important to apply proper sign conventions. Let us apply the lens maker's formula to find out the focal length of a double concave lens of glass of refractive index 1.5 placed in air and with radii of curvature 30 cm and 45 cm respectively. It is given that N2 is equal to 1.5, N1 is equal to 1, R1 is equal to minus 30 cm and R2 is equal to 45 cm. Note that since R1 is measured in the direction opposite to that of the incident ray, it is taken with a negative sign. Substituting these values in the lens maker's formula and on further simplification, we get F is equal to minus 36 cm. What happens if the lens is placed in a liquid of refractive index 1.75? Now, N1 is equal to 1.75 and all other values remain same. Substituting these values in the lens maker's formula and on further simplification, we get F is equal to 126 cm. Note that the focal length is positive. This means that a double concave lens placed in a tensor medium acts as a converging lens. Let us now look at the sign conventions we follow in case of lenses. These are similar to the ones we followed in case of spherical mirrors. All measurements are made from the optical center of the lens. Measurements made in the direction of the incident light are taken as positive, and if measured in the opposite direction, they are taken as negative. Heights in the upward direction to the principal axis are taken as positive, and in the downward direction are taken as negative. Note that the focal length is positive for a double convex lens and negative for a double concave lens. Let us see how we apply sign conventions by solving the following example. Where should an object be placed before a convex lens of focal length 10 cm to get an image that is 3 times the size of the object? In this problem, it is given that F is equal to 10 cm and M is equal to 3. M is positive if the image is erect and negative if the image is inverted. As per the thin lens formula, 1 by F is equal to 1 by V minus 1 by U. On rearranging the terms, we get V by U is equal to F by U plus F. Therefore, linear magnification M is equal to V by U which is also equal to f by u plus f. If the image is real, then minus 3 is equal to 10 by u plus 10. On simplification, we get u is equal to minus 40 by 3. If the image is virtual, then m is equal to 3. Substitute these values in the above equation, and on further simplification, we get u is equal to minus 20 by 3. A prism is an optical apparatus